just to set the scene here, I would like to begin with a brief introduction of MapleSim. One of the things that we strive to do here at Maplesoft with MapleSim in academics is to help students bridge the gap between theory from what they learned in the classroom or in a textbook to real engineering systems. And as I'm sure many of you have experienced when you were a student, and certainly I have, we get really excited about a course in the beginning, and about 2 weeks in, we're drowning in the endless equation derivation, equation manipulation, until we come to a point where the connection between equations and the system that we were originally so interested in is completely lost. So we think MapleSim is a tool that can really help students connect the two and learn in a deeper way. Let me take a step back and answer the question, well, what is MapleSim? MapleSim is a general-purpose physical modeling and simulation platform. In MapleSim, students model systems and not equations. So physical components are connected together in a way that reflects the structure of the real-world system, as opposed to structure of equation sets, which don't really give an intuitive insight to the system. The option to expose symbolic equations are available. And in MapleSim, multiple domains can all be modeled within one environment. This is important because real-world designs rarely consist of a single physical domain. So even if you're teaching only one of these topics, showing how that specific topic connects with other domains allows students to put things in perspective and understand at a system-level interaction level. Lastly, MapleSim allows students to simulate virtually and then validate physically. Simulations allow students to safely investigate a much larger range of conditions than it is possible by testing with hardware alone, and with no risk of damage to equipment, and so for a much lower cost. In software, they can analyze the system or even design a controller. Once they have their design completed and it's been analyzed and optimized, the results can then be exported to various formats, for example, C code or as an S function to Simulink or DLL to LabVIEW, where it can then be incorporated with a physical prototype for testing and further investigation. In addition to that, we recently added a CAD connector to MapleSim. So if a student has a 3D design, they can bring that into MapleSim seamlessly and begin simulating immediately. So that was just a very quick overview of MapleSim. And for those of you that are interested to learn more, we have a ton of additional resources. So we have a page on our website dedicated to engineering education content. We have a model gallery with downloadable MapleSim models from many different industries. Of course, an in-product user guide and tutorials. We have our upcoming and recorded webinars available on our website. We also have Maple Primes, which is an online community of Maple and MapleSim users where we share experiences, questions, and we also contribute to answering these as well. And of course, we have the MapleSoft team who's always happy to help. Okay, and with that, I'd like to switch gears and introduce our speaker for today, Dr. James Smith. I'm very happy to have James here today to share with us some of his experience using MapleSim in his classroom. James is an assistant lecturer at the Electrical Engineering and Computer Science Department of York University's Lassonde School of Engineering. Following the completion of his PhD in mechanical engineering at McGill University, he undertook a postdoctoral fellowship at the University of Jena's Institute for Sports Science in Jena, Germany. In a previous position at Ryerson University, he directed the undergraduate biomedical engineering program and helped lead the program to successful accreditation with the Canadian Engineering Accreditation Board. He has won teaching awards at Ryerson University as well as the University of Alberta. Dr. Smith was the recipient of 4 IEEE Real-World Engineering Project Awards from 2007 to 2010. He was also co-recipient of second place in the design competition at the 2012 Healthcare Innovation Conference at Houston, Texas. And with that, I would like to pass the mic on to James.
So what I'll do is I'll begin with an intro to MapleSim and how and why I use MapleSim. And from there, I'll talk about what spiral learning is and deductive and inductive learning and how that plays into university-level education. And then I'll talk about some specific examples with respect to doing parameter sweeping of circuits involving diodes, and then some analysis of equations for both a diode problem and an operational amplifier circuit that were used in class. From there, I'm going to wrap that up with a discussion about how the students rated their experience, and we'll see how over time, with the use of Maple and MapleSim in the classroom, student evaluations have improved, have gone up. Okay, so my background, as Bonnie was talking about, I teach at York University in general engineering and electrical engineering, and I've also taught in biomedical engineering. I've taught introductory courses on microprocessors, sensors and measurement, and instrumentation, as well as human-computer interaction. And I've gone beyond that and looked at education from a higher level, from the accreditation perspective, which is really important for engineering in Canada as well as the United States through the ABET system. In addition to that, I do work on human birth models, biomechanics, and robots, in which I've also used Maple and MapleSim. Okay, so why do I like using MapleSim? Because the work that I do involves systems. And so in my engineering work and my teaching work, I'm not typically dealing with a single domain, but multiple domains. And having tools that tie in multiple domains or have strengths in multiple domains is really important. So for thermal components and mechanical components and electrical components, those are all really important. The other thing is that a lot of the work that I do and my students do is prototyping and exploration of domains. And when we do that, we don't want to get bogged down in the mathematical analysis immediately. We want to explore and get an intuitive feeling for the systems. And so simulation products that allow us to do that first and then come back to the math afterwards is really important. And that's one of the reasons why we like using MapleSim. The university model for education is based typically on something called spiral learning, where you begin at the introductory level with some basic courses in math and physics and chemistry. And as the semesters progress from freshman year to sophomore year to junior and senior, you develop and apply those concepts in a broader and deeper way. And this is a very typical way for university education to work. So you start with basic calculus and basic physics, and you work your way all the way to the very end where you have capstone design classes and an advanced class in biomedical engineering or engineering physics and things like that. It tends to work relatively well, except when it doesn't. And what we often see with our students is that they, when they approach the sort of end of second year, the beginning of third year, and start getting to the more advanced classes, will tell us that, well, those early topics we didn't cover, or we didn't cover in depth, or maybe some professor was in sabbatical, and they had a replacement contract teacher come in, and that person didn't cover the material like they were supposed to. And so this can pose a problem when you're trying to get to these advanced topics, but the students are lacking or have forgotten some of the basics. And that's a real issue with the spiral learning model that we see so often in the university system. And what we're trying to do with MapleSim is address some of those issues. Where we find ourselves is in a third-year electrical engineering class based on an instrumentation and microprocessor background for electrical engineering students. And what they're trying to do is develop a force and angle measurement system in a lab. And they do this using an inductive learning approach, so a hands-on approach. And we apply tools like Maple and MapleSim to it. And we feel that by doing a hands-on class like this where the students are heavily involved, it tends to prepare them really, really well for the fourth-year capstone class. So it's really important that we do a good job with this class in order to prepare them for the fourth year. Now, the way classes like this are typically taught, or other classes are typically taught at university, is through a deductive learning process. And this is typically a lecturer at the front of the classroom who gives instructions on how a particular equation works. They'll refer to the textbook, and the students are supposed to infer behaviors for the systems we're talking about, whether it's a vibration system or an RLC electrical circuit, and try and come up with a model in their head that demonstrates how those equations behave. It's really a classroom first, laboratory second approach. And the opposite way of learning is something called inductive learning, and that's where the students explore ahead of time, they do lab work ahead of time, and they get to see what a system behaves like, whether it's one of these RLC circuits or a vibration spring mass system, things like that. And they explore it, and they internalize an intuitive model for how that works. And from there, they can develop the equations, etc. But basically, it's a lab first, class second approach. And this is something that a lot of schools, like the Lausanne School here at York, are starting to push, because we see that the students respond really, really well to it and learn a lot because of it. So another way of talking about inductive learning is, one approach is to give the students a system, whatever system that is. The students ask the question, how does this work, through exploration. Through that exploration, they start to ask the question, why does it work that way? And as we come into the classroom, we can discuss and question and answer, what are the rules that govern these systems? The inductive learning approach is really a natural way of learning, and we see it all the time. Kids use it all the time. If any of you have ever seen a 2-year-old or a 3-year-old using an iPad or an iPhone better than you can, they've learned it not by reading the manual, but by exploring it on their own and playing games on it and drawing and that sort of thing. It's a very, very natural way of doing it. We do it every day, and it's really something that we want to make sure our students in universities are doing as well. So to talk a little bit more specifically about how the current group of students, the millennial students, are learning and being taught in universities. They like both the inductive and deductive approach. They're used to deductive, but they also feel strongly that we should be doing more of the inductive approach to teaching. The teachers, on the other hand, tend to default to deductive because it's the way we've been doing it in universities for hundreds of years, literally hundreds of years. And in large part, this is because the inductive approach is resource intensive and it's impractical, especially if you have classrooms like I do of 500 students. But what we do see is that there's a desire on the part of the students to do the inductive approach, and they want to do a lot of learning on their own based on their own learning styles. So what we try to do, especially places like here at York, is that we try to do inductive learning with guidance, with expert guidance from the TAs and the teachers, the university professors. And what we found is that technology like MapleSim has made that choice between either teaching deductively or inductively a lot easier to do and more appropriately chosen on a case-by-case basis. Okay, so let's get into some specifics in a second here. But basically, the other thing that we need to talk about is the fact that a lot of students now are using online resources like Google to explore on their own the topics that they want to talk about in engineering and science. The problem is that a lot of these online resources are inconsistent with either the teaching approach or the teaching material that we see in class. They're either too deductive or too inductive. They're either hands-off and theory-heavy or hands-on and theory-light. And so typical examples that the students might see online are things like a circuit like this, which is insightful and descriptive. However, there won't be a lot of equations given for further exploration by the students, and the students might have a lot of difficulty trying to figure out how to link a complicated circuit like this to the simple examples they're seeing in class. And so we struggled with that problem in our instrumentation class, where we needed to have the students explore systems with accelerometers and load cells and microprocessors, and take a look at circuit components with diodes and operational amplifiers and whatnot. We started using MapleSim, and we will show you an example here of how we used MapleSim to explore temperature dependence in a circuit in a way that would be difficult to do in a regular classroom or a regular lab. We can't put the circuits in refrigerators or ovens. That'd be really difficult to do. But we can talk about temperature dependence of a circuit using MapleSim. So here's an example of a circuit that we did or the students did in MapleSim. It's a diode and a resistor. There's some current measurement going on, and there's voltage measurement across the diode. So from there, we can right-click on the resistor and take a look at sort of other parameters within it, one of them being a temperature dependence that's built into the models. And from there, we would call MapleSim from Maple in an iterative fashion and create three-dimensional graphs that show the dependence of the output current of a diode with respect to resistance and temperature. And so this is a good example of how we can use a simulation in parallel to lab activities, looking at how a diode works, to see how it works under different environmental conditions. The next thing that we wanted to do, and exploring some of the features of Maple and MapleSim even deeper, was to explore some of the math behind the circuits the students would be drawing. And again, like I alluded to earlier with the spiral model, students often were coming to this class forgetting background material. We could only explore certain cases of certain circuits because of the time that we had. Some of the math was just too complicated to cover in class, and this was limiting us in terms of the exploration that we could do in our lab components in the class. So what we needed to do was to find software, in this case MapleSim, that would help jumpstart the mathematical process, that would allow us to jump past technical hurdles that we would find with other software, that would minimize the chance of a student making basic equation derivation errors, and so they would have more success and be more positive about the lab process. The way I developed the circuit, or how to develop this particular operational amplifier circuit, is a little difficult to do on WebEx live without a lot of lag. So what I've done is I've posted the video, it's about 4 or 5 minutes, on how to do this on YouTube. And so if you follow the link that's on the bottom of the page right here, you'll be able to see the step-by-step guide for how to get this particular circuit, an op-amp circuit with negative feedback, up and running. Once that circuit was up and running, what we wanted to do was bring in an equation extraction template for the circuit. And so after we defined some particular variables like the resistor names and an output variable for voltage out of the operational amplifier, we called up Maple, and we would link in our MapleSim model using the first command here in red, and then we would put in the second command in Maple, effectively, literally, to get the equations. And using just a couple of parameters inside of that equation function, and isolating for the output voltage or the output variable called probe volt, we're able to get the equation that defines the characteristic behavior of that negative feedback operational amplifier circuit. And for anybody that's seen operational amplifier circuits like this one in particular, you'll see that the form for the circuit is very much like you would see in a textbook. And so this is really, really positive in terms of what the students would be exploring with, because the consistency between what they're doing in their simulation package, in their lab activity, and what they see in the classroom or most online examples is there. The consistency is key. So what we end up seeing is that the probe voltage is equal to the negative ratio of the two resistors multiplied by the input voltage. And you take any standard electrical engineering textbook and you look at the circuit that they've got in there, and it has the same form, same basic variable names as you would see in MapleSim. So students really like this. This was a key thing for them to see, that this was a constructive tool for them to use. Now that equation was pretty simple, and hand deriving it, not so bad. What we also showed the students was that you could take a seemingly simple circuit and see the complex mathematical behaviors or aspects that underlie its behavior. And so we took that initial resistor diode circuit, we ran it again through the same process we did for the op-amp, and you'll see just from the number of variables in the equation that came out, it's a far more complex but also more subtle behavior in that particular circuit. And so what was important about this was that the complexity would initially be really intimidating, but because we could be confident in our tools and the students could see the behavior in the numerical simulations as well as in the actual circuit that they had in class, we could take a look at this piecewise output for the diode behavior, and we could have a discussion about what each of those variables meant and why they were set up that particular way. So it was a really good way to prompt discussion in the class. So what we want to sort of emphasize here is that Maple and MapleSim as tools have really encouraged the use of inductive learning and to make it successful within our classroom. We know that the students want to explore on their own, but they also want to have expert guidance. That's why they're in college or university, because they want access to the experts. They also want to go beyond the simple textbook examples. They want to add on an extra resistor or an extra spring into a spring mass system or an extra damper or two and want to see how that behaves, but it might not look like what's in that textbook. They want to go beyond. The fact that they can do equation generation from a GUI schematic is fantastic, and it works the way that they want to work. And one of the side benefits to all this was that the students started exploring other features of Maple, one of them being the clickable math feature in Maple, which was really enlightening for me. And what we're seeing really is that there's a transformational process that's going on in the engineering education system now. And it's similar to that transition many years ago between slide rules and calculators. What we're seeing is that we can go beyond what a simple handheld calculator or a simple computer calculator can do, and we can explore in a much broader and deeper way than we ever could before. And this is really encouraging from a university education perspective. What have the students said about this? Well, they said things like this. We learn the material through the labs, and from the labs we would learn the theory. The process of inductive learning from labs to classroom was something that they got and they understood and they were positive about. Again, the labs made me learn the material before the lectures. They were doing this. And if any of you have taught at a university level before, you'll know that it's really hard to get the students to do any work before a lecture. And yet the students were positive and encouraged and enabled to do so. The students understood the why of the material they were learning through the labs, in the labs through the theory presented in the lectures. So really they are closing the circle, closing the loop between the labs and the lectures, and it's really, really successful with them. And the numbers don't lie. What we were seeing here in terms of quantified student feedback was that in 2010, we weren't using Maple and MapleSim. We introduced Maple and MapleSim into the classroom in 2011. It took us one semester to get our feet wet with it, to get our sea legs, as it were. And by 2012, the feedback from students was getting more positive. 2013, 2014, even more so, to the point where we can't get any more positive with the students. They're reaching 100% satisfaction with the way the concepts are being explained in class and how it helps them personally to learn the material. So really honestly, the students groaned when we told them we were going to be introducing a new software package, but through practice in class and labs, they were really wowed by the fact they could do equation generation so easily in MapleSim. And the context-aware math, the clickable math that they were able to see in Maple was also super positive for them. In fact, it was so positive that we had an unintended consequence to this, where the students were bringing those tools from our instrumentation class into the controls engineering class. The students were doing it naturally, organically, and they were seeing that the stuff that they were doing in Maple and MapleSim, or the things they could explore there, looked like the theory not only in their instrumentation class, but also their control systems class. And then the students were teaching me at the same time. They introduced me to the code edit blocks, the code editor within Maple that I hadn't used before. So they were really positive about this process. So in conclusion, I wanted to say that basically we see most, in a lot of the university programs, that the spiral model in which we rely on can break really easily. It often works really well, but on occasion it can break. And so having tools that help us fix that or bridge that gap is really important. Inductive learning is one of the new ways of learning within engineering and science, and we need tools that complement that approach. We also note that bringing software into the classroom or technology into the classroom has not resulted in less use of our instructors, but we've seen that the role of the instructors has gone from sage on stage type of instructors to guide on the side kind of approaching. And the students respond really, really well to that. We've seen that if students aren't experts or if they're rusty in a particular domain, software like MapleSim has been fantastic to get the students up and running. It's been really good for me as well. The context awareness has been super helpful, and the familiar format of the equations that come out is key. that consistency has been really, really good, really important, and reinforcing for the use of this tool. The students have responded really well to this approach, as we can see from the classroom feedback, and we're looking at other extensions into, say, distance education and things like that.